Hello, welcome back to three-phase circuit analysis. We're covering Delta-Wye circuit problems. This is the part one, the first problem that we're going to cover in our sequence. It's a really good problem because it's very practical. It's very representative of what you might actually see on an exam. So let's take a look at what we have. First of all, you have this circuit diagram, which looks a little bit weird. We'll talk about it a little bit more in a second. But believe it or not, this is actually a delta source is what this is. You know it's a source because you see you have three sources, so you know you have three phases. You have three impedances. You have an impedance associated with this source, an impedance associated with this source, and an impedance associated with this source. You notice that all three of these impedances are the same, so you have 2.7 ohms for the real part, and the inductive part is 13.5 ohms. So because they're all the same, you know it's a balanced source. Now you look at the, or the impedances are balanced anyway, and then you look at the sources themselves. 4156 is the magnitude in all three cases, and then you have 0 degrees and you have the plus minus 120 there. So because you have all three phases of the source impedances the same, and because the source voltages have the same magnitude but their phases are just different by 120, then you have a balanced three-phase source. You know that this is not a Y source because a Y source looks very different than this. I mean, even if you don't draw it as an actual Y, there's always a central point in a Y source that's the neutral terminal. So whether or not it's flattened or whatever, you can always tell very easily if it's a Y source. But in here, there is no central point, really. I mean, you might think this is a central point, but this central point doesn't touch this source at all. This is connected over to the outside. So I'm going to prove it to you in a second, but this is a flattened out delta source, right? So typically when you draw a delta source, not always, but typically you'll draw it like this. You will sometimes draw it in a triangle fashion. That's fine. But sometimes I'll try to trip you up and draw it like this. So this is a delta source. And then it tells us that this delta source is connected to a Y load. So we have a delta source. We have not drawn it, but it's connected to a Y load. The line impedance, here we have the three lines A, B, and C. The line impedance is 9.1 plus J 71.56 ohms per phase. That's just giving you the line impedance of all three phases without drawing the lines. And it says it's connected to a load, and each phase of the load is 1910 minus J 636 ohms. So you can see that the load actually is a capacitive component because of the negative sign. And we have the real part here as well. So you have this delta source. It's connected, the three transmission lines are connected to the same line impedance which is given here. And then on the other side, which we haven't drawn, we have a Y connected load, which would be, you know, we could draw it all, but what the point is that you're not always going to have it drawn for you. In fact, a lot of times you won't. It'll just give you some information, they'll tell you something else about the loads and the lines, and you'll just have to kind of use what you have. Of course, we could draw this, and we could draw the Y load. That would be fine. But in this particular case, we don't need to. Now let's take a look at what we're actually asked to find. First step is draw a single-phase equivalent circuit. Okay, we know how to do that. We'll do it in a second. And we want to find the magnitude of the line voltage at the load terminals. Now you see why terminology is so important. Magnitude means we don't care about the phase angle of whatever it is we're asked to find. And we're trying to find the line voltage, which means what? Line to line voltage, so VAB for instance. But at the load terminals. Now we haven't even drawn the load, so you know you have to use your imagination or you draw it yourself on your paper. But anyway, you have this delta source is connected to a load. You know you're going to have an A, B, and a C terminal. So what this is asking you to do is you want to find that line voltage, VAB, right? But the magnitude only of it, right? So that's what we're trying to find for part B. Part C, find the magnitude of the phase current in the delta source. So this is a delta source, and we want to find the magnitude of the phase current. So remember, what's the phase current? It's the current going through each branch of that triangle in the delta, because that's each phase is one of the legs of the triangle, so we want to find what the current is through each leg of that triangle. Now this triangle's flattened, and I'll explain why in a second, but basically you're asked to find, this would be a phase current through one of the phases, this would be a phase current through another phase, and this one through here would be a phase current through the third phase. So you're trying to find the phase current. In this case, it tells you only want the magnitude. So when you're asked to find the magnitude, you don't have to find A, B, and C phases because all the magnitudes are going to be the same for the line currents and the phase currents. So you just have to find the magnitude for one of them, and that's going to be the same magnitude as the other two. Finally, we want to find the magnitude of the line voltage at the source terminals. So just like we found the line voltage at the load, now we're asked to find the line voltage at the source. So this one's actually drawn here since we have the source. The line voltage, which is another way of saying line to line voltage, would be, for instance, VAB.